Excuse me, let me zoom again. Okay, covered by a vapor film. But you have already seen this, like if the surface is covered by the vapor film, we see the detrimental effects of that on heat transfer. But then what's going on here? We are having increasing heat flux. As we further increase the temperature. And the question is why? Any guesses on that? If you are following this from the textbook, it's already there. So what you can reason about that, right? So look at the temperature range here, 120,000, that's logarithmic plot. We are actually having quite a high temperature values here. And remember that one of the modes of heat transfer was particularly important for high temperatures, like astronomically high temperatures, for instance, right? This was thermal radiation that we are going to be talking about in the second half of our semester. And that's also the reason why we are going to have effectively enhanced heat transfer. The heat transfer by radiation becomes important. And but let me write a small comment about this boiling crisis, or at least hint about that. So we have already mentioned that getting to this film boiling regime is not straightforward. Like we cannot simply, um, you can actually increase the heat flux, because if you do that, you are going to actually suddenly jump from point C to E. Look at the temperature range. You are going to burn whatever you have in your system. So the heat flux control is not straightforward. Excessively large temperature differences, this excess temperature. Okay, so now we have enough information as thermal engineers to design our systems responsibly. So what do you think is the most appropriate regime in the curve? Oh, I should bring the curve here. The, the most appropriate regime in this boiling curve, let me start a poll online, and while your friends online are answering the questions, I think that I should add one more option here. As they're answering, at the same time, I think the class participants may want to quickly start thinking about that. So what regime of the boiling curve you should be operating your heat exchanger, for instance, boiler? That's probably the last conceptual aspect in this, boiling discussion before we jump into the correlations and do some calculations. So I think that's kind of important to realize. So remember Nukuyamas experiments. I'm also seeing the same pattern in the reboot session. I can see the answers here. So what was the problem in Nukuyamas experiment? it's easier for you to reply, guys. So anyone remember what is the main problem? Yes, jump, right? This boiling crisis, exactly. So this jump melted away his specimens. Iron melted, nichrome melted, any metal without an excessively high, the melting point is going to melt down. So you don't want to be there. Is that right? So if you and most practical applications are also controlled by heat flux. Remember that controlling surface temperature is difficult. We have seen this in flat plate discussion as well, right? In order to control the surface temperature and make it an isothermal surface, we had to attach various heating modules with different heat fluxes all across a plate. You might go back and look at our example problems that we solved in class last semester. Because if you are keeping the surface temperature constant, then you are going to need a variable heat flux. But most of the time, our heat transfer equipments are capable of providing constant heat flux. So, so when I look at the results, and there are not many people in the class anyway, so let me publish the poll, and let me also take a quick screenshot of this and post it here. So that's what we got. The correct answer is between P and C. That's the optimal location. And but again, I think if you have any doubts, please go back to our discussion. And remember that anything above C is not going to work. This is the optimal regime. And this is actually corresponding to the maximum heat convection heat transfer coefficient that you can get before achieving maximum, this critical heat flux. Of course, you can get higher H's in the film boiling regime when you consider radiation together, but you don't want to be there for most applications. Let me briefly write down what I discussed. And this boiling crisis, meaning that this excessive jump in temperature when you increase the heat flux above the critical heat flux, has detrimental effects on system integrity, meaning that things are going to melt away, right? System integrity. The point C is called the burnout point. Okay. Any questions about what we have discussed so far? At this point, I believe you're equipped with a very good understanding of the conceptual aspect of this boiling problem. We have investigated all the regimes. Now I would like to talk about some heat transfer correlations. And one of the most important one for us is nucleate boiling, because what I described as the optimal regime is within the nucleate boiling. So let's write down the heat transfer correlations for saturated pool boiling. And the main mechanism behind the nuclear boiling is that the local force convection phenomena, right? So let me also write this down. Let's nucleate boiling. So the bubbles are forming. One side effect of them is they are moving up, recruiting more liquid. That means near the surface, there is this flow induced by bubble motion. And this flow is actually creating some form of force convection near the surface. Why am I saying that? Because we know how to treat force convection. We have learned about it. I'm having extra difficulty today with my tablet screen associated with. Okay, so that's the mechanism. And we know that the typical correlation for Nusselt number in that case is it is a function of Reynolds and Prandtl number through a power law relationship with C, a coefficient, Reynolds number raised to the power some exponent m, Prandtl number raised to the power some exponent n. However, the length scales, what are the length scales here? What is the characteristic of this flow? This force convection, remember when we discussed free convection, we came up with a length scale for velocity, I'm sorry, scale for velocity, u0. So you need to do a similar analysis. And in that case, you need to describe what is the size of an average bubble formation. That's going to depend on the surface tension as well. And your textbook is actually going through some detailed explanation about defining the scales in the problem and applying, some form of the C Reynolds number, Prandtl number, power law relationship. And at the end, we are going to obtain a correlation. So I'm not going to go through that. I don't expect you to know the details of how you obtain this correlation, but I expect you to know how to use this correlation and what are the particulars of practical applications of that. This correlation is due to Rosenov. That's one of the most frequently used correlations that we're also going to be using in this class. And that's equation 10.5. There are a few parameters in this correlation. We can see that latent heat of fusion here, the liquid dynamic viscosity, density differences, surface tension right over here, specific heat, some coefficient CFS. That's actually the coefficient in the beginning of Reynolds number and Prandtl number relationship, some modified coefficient. And there is a Prandtl number raised to the power n, right? So these are the two things that we need to determine. But before that, let's discuss at what temperatures we are evaluating the properties. So all properties are evaluated, all properties of the liquid are evaluated for saturated liquid. Based on saturated liquid at this T saturation, whatever saturation temperature you are working with. Okay, but there's one parameter over here, density of the vapor. That's clearly a vapor property. So we are going to evaluate that at except density of vapor, that will be evaluated as saturated vapor at the same temperature. So we are either evaluating the properties as saturated liquid, most of them are saturated liquid, only this density of vapor at saturated vapor condition. All right, so there is the surface tension that we don't know yet where to obtain, but it is if you look at the back of your textbook, surface tension, just like other properties, surface tension is a property of a liquid. It's a thermodynamic property of a liquid in particular. And it has units of Newton meters, and you can find it in this table for various liquids. Water is not here because we have a more detailed table for water, as you know. If you look at a table 8.6, it was, I think, the last column, something like that. You are going to find that surface tension is there. Oh, I missed John's question. I'm sorry about that, John. I think during the discussion of boiling crisis, John was asking, without the metallurgical concerns, would regime between D and E be a good also? So I would say yes. So there are some applications of that as well. So if your surface can withstand, yes, you can go into the film boiling regime, and we are going to be discussing some correlations about that as well. But in that case, we are going to need to take into account the radiation, so it's not pure convection. Okay, so what else about this? Oh, I didn't even mention how we obtain these two parameters, CFS and Prandtl number. So it turns out that these parameters, when I was describing the nucleate pool boiling, I said that the bubble formation, the bubbles form at nucleation sites. What are those nucleation sites? They are often impurities on the surface or some roughness, some cusp points on the surface that are going to serve as nucleation sites for bubbles. I don't exactly remember. One of you actually at the end of the class asked me a question. I think it was this section. And the question was how all those vapor particles, like vapor molecules, are coming together and forming bubbles if they are forming all across the surface. And I described like, okay, so I don't exactly know the reason, but water has some, strong properties like hydrogen bonds, van der Waals bonds. What was it? Okay, so I'm sorry, I'm not very good with faces, so I might remember you guys from time. I must forget your faces. But actually, the other explanation is that the bubbles are not forming everywhere. They are starting forming at nucleation sites, and therefore vapors are forming close to each other in any way. They are going to start from one location, and then this bubble is going to grow at that location. So therefore, depending on the surface conditions, the density of nucleation sites are going to change. And as a result, these parameters CFS and N are dependent on these surface conditions. You can have polished or etched surfaces, different. Also, they depend on surface tension. So this also what kind of surface fluid pair you have is going to affect these parameters. But you can look up from this table A 10.1. These are surface tension. Nucleation sites on surface, finish, and so on. Okay, so I think that's clear. But another observation from this correlation is that heat flux is proportional to the temperature, excess temperature raised to the power 3. So if you somehow know the excess temperature, would like to calculate the heat flux, the uncertainty in your excess temperature is going to actually propagate and be quite large when you calculate heat flux. So that's not the recommended way to calculate heat flux, or let me put it this way, if you do this, know that this is not very accurate. Let me call it less accurate. Compared to what? If you know the heat flux and you would like to calculate the excess temperature, So any uncertainties in the heat flux is going to get diminished as you take the third route. So this is going to be more accurate. And that's the recommended way you would use the Rosenau correlation. Okay, so that's heat flux, and that heat flux can occur at any excess temperature as long as we are in the nucleate pool boiling. But then there's other important parameter that's a single value, right? That was the maximum heat flux or the critical heat flux. Critical heat flux. And this is a correlation for critical heat flux. The accuracy is approximately 16% is reported. And we have again coefficients here. So these coefficients C turns out to be pi over 24. That's approximately equal to 0.131. This is for cylinders like a wire or spheres like particles, small particles that are being, let's say, dropped in water during quenching, for instance, right? They're going to cause local boiling of water around. Or the parameter of 0.149 works better for flat plates. Okay. So the next one is, let me write, transition regime. Well, transition regime itself is not very important for us because, as we said, they are not easily accessible. However, minimum heat flux is important. You know that in transition regime, the convection coefficient is going to decrease. Let me move this down a little bit. By the way, unless otherwise is noted, the same way that you evaluate the properties work here as well, except for the vapor properties, evaluate them at the saturated liquid. And for the vapor, you are going to evaluate them based on saturated vapor state at the same temperature. And this correlation for minimum heat flux is for a large horizontal plate. In the literature, this correlation is reported for other surfaces as well. However, for our purposes, you can use this correlation with a number of 0.09 as a C, and accuracy is not great, so it's around 50%. You get kind of a ballpark estimate of the minimum heat flux. Why is this important? Let me, motivate you by writing just under that. When this heat flux drops below this minimum heat flux, the vapor film in the film boiling is going to collapse, and we are going to reestablish nucleate boiling. Okay. Okay, so there are a couple of questions before I move on with film boiling. So generally asking, is there specific numerical criteria for us to decide that the boiling type is nucleate boiling? A good question. So for water, yes, and that's based on the boiling curve. And if you look at the boiling curve, you are going to be able to tell for which temperature range or what kind of heat flux ranges you are going to be obtaining, nucleate boiling. But of course, heat flux itself is not going to directly give you the result because the temperature is multivalued if you consider that axis. So the excess temperature knowledge, either as an assumption that you assume in the beginning of your analysis or directly known from your problem, can actually describe you what kind of conditions you obtain for the boiling regime. Ahmet Emir is asking, does this mean that there can be abrupt, jumps in heat flux? So heat flux itself, it depends on how you are going in. So the story is, when you look at this curve again, let's go back to this curve. So we are controlling the heat flux. The heat flux is not jumping. We are sustaining the same heat flux. The jump occurs in the temperature. And then when you go back from here by decreasing the heat flux, again, the heat flux is not decreasing, but the jump occurs back in the temperature and you go back to nucleate boiling. That means vapor film condenses from D and you find yourself somewhere between A and B with the isolated bubbles. And then when you further increase or decrease the heat flux, you are going to be going up and down in this curve, right? So this is kind of the story behind that. Okay, great. So this is somewhat like actually tracing a process in thermodynamic, a thermodynamic process in a diagram, right? So it is similar to that. Let's talk about film boiling. Okay, so things are a little bit different here. Well, remember that this film boiling takes the name from this vapor film forming on the surface. And the characteristics of this vapor film is quite similar to what happens with film condensation. We haven't covered that. Let me bring in the correlation, by the way. So this is the correlation we are going to be using. We haven't covered film condensation yet. We are going to be covering next week. And you are going to encounter a very similar equation. Because the phenomena physically similar, so film boiling phenomena can be interpreted as the reverse of film condensation, but plus the radiation. And so we have a few parameters here. First of all, by the way, so let me write this. This is analogous to so don't be surprised when you see a similar equation when we discuss condensation. So C has multiple values. It can be 0.62 for a cylinder and 0.67 for a sphere. Okay. And clearly the characteristic length here is D, right? It's diameter of the sphere or cylinder. The other thing over here is HFG with a prime. So now the temperature differences are becoming quite right, that Ts minus T saturation are getting high. And if you remember in the beginning of the chapter, the sensible heat effect due to the temperature difference, Jacob number, is very small, much less than 1 compared to the latent heat effects. That's why the Jacob number is very small. But with the increasing temperature, we kind of have this vapor film that's superheated vapor now, and it's very hot. So it actually has received some contribution in terms of sensible heat. So therefore, in order to take into account the sensible heat effect of the elevated temperature of the vapor, we are modifying the latent heat of vaporization. We are augmenting it with a term. That's 0.80 times the specific heat of volume, vapor, and vapor multiplied by this temperature difference. That's actually excess temperature, right? So that's sensible heat contribution. Since the temperature of the vapor film overall is greater than saturation temperature, is actually much greater than. If you look at the chart, it is going all the way to the thousands. So then it is the question, how do you evaluate the properties? So now this is developed based on film condensation. We are considering the variation of actual formation of a boundary layer over a surface. And therefore, the temperature of the film is going to be somewhere between the surface temperature and saturation temperature. We are evaluating our properties at the film temperature. That's what we are doing, but except there is one aspect, liquid. There are liquid here and also HFG. They are evaluated at simply saturation temperature and for the saturated liquid, right? So I think it's implicitly implied. Before we take a break, I would like to finish this discussion. So if the temperature of the surface is greater than 300 degrees Celsius, at this point, the radiation effects becomes important. This correlation does not provide you this contribution. That's simply giving us the convection. Anyway, I couldn't change the color. I will change. Okay, so this is actually the convection heat transfer coefficient. It doesn't include radiation, but what you can do is here, you can actually come up with an overall coefficient that is combining those two coefficients and use that in your calculations. The average total coefficient is going to be, that's raised to the power 3/4. That. So in most general case, if you need to take into account, you calculate this convection heat transfer coefficient from this correlation above, and then you calculate the radiation heat transfer coefficient in a typical way. We know that's a strong function of temperature. But in the most general sense, there's also a 4/3 parameter here. And this is an implicit equation. So what you need to do is solve for H bar. You will need to do that. So that's a root finding problem, right? You are going to substitute the numbers and then find the root of the equation, putting all the terms on one side, find the root of that equation. Well, if the radiation heat transfer coefficient turns out to be much smaller than, let's just simply say smaller than convection heat transfer coefficient, then you can simplify this expression and come up with an explicit way to calculate the total coefficient. (3/4) H radiation. So now that's explicit, right? The H only shows up on one side of the equation. So you can calculate that. Any questions about? Yeah, I'm going to solve some example problems today. So some aspects may become more clear during that time. If you don't have any questions, how about I'm going to take a short break today so that we can actually solve all the problems I intend to. 5-minute break, and once we come back, we are going to discuss a few remarks and then start solving examples.